All right, guys, welcome to another episode of Cuda Education. Today, I just want to do a quick overview of a brand new script that we're going to be investigating. This is called compute headless.cpp, and it is purely a computational algorithm. So we're not doing anything graphical this time around. It's purely just highlighting the compute capabilities of the Vulkan API. This is just a quick overview video, so we're not going to get into details. We're just going to kind of run through the script, see what catches our interest, and keep it moving. You know, we have kind of finished with the compute colon load script for now. We've done everything we can with that. We've sort of investigated the core pieces of that algorithm. So we move on to the next inline. Now, if you guys want to be able to run these examples on your machine, you need a Windows-based machine with a Vulkan-capable GPU. Um, Preferably NVIDIA GPUs, simply because the tools that we use, like some of the other debugging and graphics investigation tools that we use, profiling, all that stuff, um, they're NVIDIA GPU only tools. So if you get tutorial number 1, which installs the Vulkan SDK, and tutorial number 13, which walks you through installing the Vulkan examples. All of these examples here. Now, if you want to be able to run the ray tracing examples, all these ray tracing examples, you will need to make sure your GPU is also ray tracing capable. For the NVIDIA family, it is RTX series and later. AMD and Intel, I have no clue. But you do not need it for this example or the previous compute colon load examples. Basically, it's only for these examples here. Everything else you could basically run on a Vulkan capable GPU that doesn't have ray tracing capabilities. All right. So we are at the compute headless.cpp script, and basically all it is you input a bunch of numbers. This is Vulkan validation stuff. I have some validation stuff going on, but we're gonna ignore that for now. But we input a bunch of numbers, and then we output the numbers basically with it uh, basically adding the two previous numbers together. So we have 0, we have 1, and then we have 1 again because 1 plus 0 is 1, and then we have 2 here because 1 plus 1 is 2, and then we have 3 here because 2 plus 1 is 3, and then we have 5 because 3 plus 2 is 5, and we have 8 because 5 plus 3 is 8, and we continue, right? Um, we have 13 because 8 plus 5 is 13. We have 21 because 13 plus 8 is 21, and we continue. And that's pretty much the heart of what this compute does. Now I will say, it's a little scary because there's a lot of boilerplate and stuff just to get this simple thing going, but it's not too bad, right? I know it looks a little scary, but to achieve this, we're at 600 plus lines of code, right? But a lot of it is just boilerplate stuff. It's just making sure your setup is correct, making sure you have the proper features on your GPU to do it, all of that stuff, right? Believe me, it's not too bad, right? But we will have to spend a little time just going through the ins and outs of it and appreciating all that's going on. So um, yeah, let's just run through it. I don't want this video to be too long, so we're just gonna run through it. So um, we basically have a bunch of includes assets that we need. Um, we set up our Vulkan example class. Um, we create a buffer backing up the buffer handle. So create a buffer, create buffer handle, create memory backing up the buffer handle, right? So basically this, what this is doing now, so we go from here to here, create buffer. So we're basically creating a buffer and then right, and then we're looking for a memory type that fits the buffer, the properties of the buffer that we want, right? So we create the buffer, and then we have to find the memory type that matches that. So we have a for loop where we're going through all of the memory properties, and we're finding one that matches the memory that we need for our buffer capabilities, right? Again, we're not going to go through it too much. Once you find a proper memory, you allocate that memory. Um, and then I guess you map the memory to the GPU, right? So VK map memory, it's we're moving memory somewhere, okay? But we'll get into that later. All right, so we do use for this particular example, we do use shaders. I'm not sure whether it's a GLSL or the slang shaders that we actually use for what's running on my machine. But again, guys, you know that shaders are instructions that basically run on the GPU. So this source code is on the CPU. It's sort of managing, everything and whatever, but it's issuing commands, and then the shaders manage, processing on the GPU. Now, GLSL is normally what we have been using in all of our examples, but here we make accommodations for slang. Now, slang is a new or shader language. Not to go on a tangent, but a lot of innovation in sort of graphics processing and computer graphics is associated with the shader portion of the language, right? So Vulkan API is like the foundation. It's like the foundation of the skyscraper, and then like the innovative stuff. A lot of times is lives on the shader side. So it lives on the GPU. It lives in GPU processing, and that's why you find these different shader languages: GLSL, HSLSL, and slang. And these are in charge a lot of times with innovating stuff. You don't necessarily want the foundation of your skyscraper to be innovating, because then the whole thing collapses and you get instability in your system and errors and stuff. However, for the shaders, you could which is maybe like the penthouse and stuff, you could experiment with stuff, because it's tangential to the core, it's not the core itself. So anyway, we make accommodations for slang. Slang can only run with a certain core of Vulkan. So like the foundation of the skyscraper, slang can only run on a certain foundation of the skyscraper. So a certain core of the language, that's what slang is. We get into instance creation. Yeah, we get into a little bit of instance creation. And then right, check if layers are available. So this is the Vulkan validation stuff, right? So um, I guess I have it on, but so it will turn on the Vulkan validation, and if it's available, it sets layer available to true. Otherwise, it's false, right? Um, and then if layer is available, so if we do have Vulkan validation layers, um, we add certain extensions to the instance, right? So you will see this theme going forward where we check for a capability and then we add extensions to our instance so that it runs with our instance. Okay. Um, this is if guys are running Molten VK, which is the Mac OS port of Vulkan, so Vulkan can run on the Mac operating system. Realize, guys, that Vulkan is operating system agnostic, so it's not proprietary to any particular operating system. I'm sure it can run on Linux, Unix, um, ARM devices, Mac OS, Windows, all that stuff, right? The Kronos Group Consortium is sort of independent of any particular um, OS maker or operating system maker or what have you. Okay, so doesn't really apply to me because I'm running Windows, right? Right. So we could skip that. Okay. Um, Again, we're doing some stuff if the layer is available, and yeah, I may or may not discuss this, but I mean, I guess I need to at some point because it's an important part of Vulkan, right? Device creation, physical device always use first. We have to figure out what GPU we're using and what are the capabilities of the GPU. So we have GPU here. Does it tell us in the when we run the script? Okay, so we have GPU NVIDIA GeForce RTX 4050 laptop GPU, right? So let's compute example, and it tells us what GPU we're running. So this is all part of the physical device. That was this right here. Okay. Um, Request a single compute queue. So we need to know if the compute queue is yeah, we're basically testing to see if it has a compute capability, right? I mean, obviously it does, but we have to test for it. And then if it does have that, then we assign the queue family index to that particular you know queue family index, and then we break out of the loop, which is obviously we would do that because we've now found what we're looking for. Create logical device. Um, Again, this slang thing where you need a specific version of spare V, which is part of the Vulkan 1.0 or greater. So device extensions. So notice that we have device extensions here, which is like GPU related stuff, and then we have instance extensions. So in instance extensions and device extensions. Okay, we'll get into that a little later. More Mac stuff. Um, so we get the compute queue. I guess we put it in the queue variable, and then the compute command pool. We need the command pool for the command buffer. Um, all right, so now we're filling in prepare storage buffer, compute input buffer elements. Yeah, we'll have to investigate this stuff. Fill input data. So again, guys, the input data is simply a bunch of numbers, right? That's all the input data is. Um, all right, this is cool, but I'm not sure how it knows when to stop. So here we create, we figure out what the buffer size is based on the number of, is buffer 324, is buffer elements. Okay, so buffer elements is 32. All right. All right, so buffer elements is 32. So we at least know that we're unsigned integer, 32 elements. So 32 elements times, you know, the size of one unsigned integer, right? So that makes sense. Copying the data to VRAM using a staging buffer, right? So I have stuff on this, but basically you do a staging buffer process where you have to move the data over from CPU over into GPU, right? So when you see VRAM, generally it means memory on the GPU, right? So we have to do a staging buffer process to do that. Create the buffer, put in your flags. You guys know about the flags, right? Transfer, and host visible. Um, we create another buffer again. I guess right. So this is the CPU side and this is the GPU side. Notice that we have memory property device local bit. Here is memory property host visible, device local bit. So this tells you, this device local bit flag tells you that it's GPU side, right? So CPU GPU side. Um, we do the staging buffer operation. Prepare compute pipeline. So we have descriptor pool, which means we're gonna eventually have descriptor set stuff. Um, Pipeline layout stuff, pipeline cache, create pipeline. Um, we'll have to look up this pipeline cache stuff. I don't fully remember what it is about. Descriptor set stuff. We know we have descriptor. Anytime we see descriptor pool, we know we're creating a descriptor set of some kind. Lowercase vk is always important. Um, yeah, this vk create pipeline cache we'll have to investigate. Let's see. Create a buffer for compute operations. Fence for compute. Command buffer sync. So anytime we see fences, guys, we know that we're dealing with CPU to GPU synchronization. We will get into that. Barrier to ensure that the input buffer transfer is finished before compute shader reads from it. Mm, right, so it does a pipeline barrier in order to do that. We'll have to investigate. I really actually haven't really talked much about pipeline barriers. That's definitely something I need to spend more time with. Um, Barrier to ensure the shader writes are finished before it writes. So that's right. So this is another sync thing. Right. So the shader is doing the calculation, the shader is doing the operation, but we have to make sure that the shader has done its calculation before we try to read back information to the screen or whatever, I would say. um all right, so we're transferring We're transferring the results back to the CPU. Is that what we're doing? Yeah, maybe we're transferring results back to the CPU. I'm not sure what's going on here, but read back to host visible buffer. Why would the why would the host be reading back the results? Wouldn't you just display it to the screen? I don't know. I'll have to figure it out. Submit compute work. I'll have to figure out all that's going on here. Make device rights visible to the host. So we have this map memory thing again where we're doing something with the CPU and GPU, right? Anytime we see VK map memory, we know that's what's at task. Output contents. Are we outputting? I guess we're outputting the content. So, all right, all right. I get it. My bad. I get it. Okay, so the thing about it is that this is not this text stuff is not it's not being displayed by the GPU. It's being displayed by the CPU. I remember now. My bad, guys. Okay, so we generate a bunch of data, right, on the CPU. We push the data over to the GPU, right, with the map memory and the transfer, the create buffer and the staging buffer and the transfer over to the GPU. So we create an array of numbers on the CPU. We transfer it over to the GPU. We have the GPU do some calculations like we outlined, right? The GPU does the calculations and it gives us back this information, right? But the thing is that we are only this is a strictly a compute queue situation. So because it's compute only, we don't have any way of graphically showing stuff to the screen from the GPU, right? We can't show stuff to the screen from the GPU because we are only dealing with the compute queue. So in order for us to display stuff to the screen, we have to bring it back to we have to bring it back to we have to bring it back to the CPU. And that's why you see here, where is it? That's why you see here all this log stuff, right? We have never really done anything with this log compute input, compute output, right? We've never really done anything with this log function, right? This is a CPU side function for us to display to the screen. We have never seen that in any of the examples up to this point, or really any of the other examples, if I remember correctly, right? This is a CPU side thing because most of the other examples we're displaying stuff from the GPU. The GPU is in charge of displaying to the screen, which means you guys know we have the swap chain behind that and all of that and all of that, right? But here there is no the GPU doesn't have the capability to display to the screen, so we have to shuttle information back to the CPU in order for us to display to the screen. So that's why you see all this log stuff, right? Then we clean up, we destroy a bunch of stuff, we run a bunch of destructors, and we made it to the end, guys. Yeah, not my favorite example. I'll tell you that much. I mean, for what we're trying to accomplish, it's a lot going on. I mean, I don't care who you are. This is a lot, right? Just to get this. But again, let's not be ungrateful. This is actually a blessing because you have control over everything that's happening basically on the GPU and the CPU, right? Vulkan gives us that control, but with the control, there is a lot of instruction, okay? But we are brave people. We are diligent people. We are going to plow through it and try and learn as much as we can with this example. But yes, it is not my favorite example, right? Um, but we have to learn it. We have to understand what's going on. Just get a good grasp of of all that's going on. Shuttling memory and buffers and data from CPU to GPU and then back to the CPU so we can display. All right. So this is Cuda Education, guys. Thank you for watching. Definitely make good use of 2026. It's a brand new year. You have 12 months to move yourself into a better place. So learn some computer graphics, right? It can't hurt you. This is where the world is going, and it's time well spent. Thank you guys for watching. Have a great day.